Yes.
Are we talking about mentally or physically or emotionally or what are we talking about?
I'm ready to torture you with trig derivatives.
You're emotionally ready.
I am not emotionally ready for that.
So, our goal today is to find the derivatives of all the trig functions. So far we only know one.
Today?
Yeah, we know one. We haven't made a note card for it.
No, I mean like we're going to learn them all today.
Yes. And apply the derivative of trig functions to harmonic motion.
Harmonic motion.
Math. Music.
Yeah.
So what trig derivative do we already know?
Sine.
Derivative of sine is cosine.
Yep, I knew that.
Does that mean that the cosine of sine, or the derivative of cosine is sine?
Close.
Close.
He's actually very close. The derivative of cosine is negative sine.
Wait, what does negative sign look like?
I will show you. Let's look at graphically and I'll show you.
She's side, you know what that means?
That means I hadn't prepared for that question, and so I have to do a little more thinking than normal.
That's what it means. I was gonna say something else, but if that's what it means, then why change it?
Or maybe she's lying to hide the true purpose.
A lot of people don't like trig, but it has its uses.
It's fun, but
Did you say it has its uses or it has its uses?
it's fun, but it's very confusing
You asked me anything
too.
about it, and I was there, you were trying to be didn't go well.
Okay, did everyone get the objective written down?
Yes.
So since we,
I don't know.
we don't really need that since I already talked about the derivative of cosine.
What did you do? Oh, that's what you did.
So let's consider then the graph of cosine. Ooh. So we know cosine. Can I actually enter functions in? Maybe not. I was kind of excited. This is the first time I've used this.
Go to the third one.
No. Alright, anyway. So we know graph of cosine starts at 0 or 1. Graph of cosine starts at 1. Graph of cosine starts. And just to make this a little bigger, I'm going to actually draw 1 here. So, just so we
That's
can...
cool.
You should like change it so you say one, so that way I'm not like super confused.
Just draw it on your paper as one.
Just ignore the...
Numbers? Can you give it there?
Yay!
Okay,
Okay.
that's better. Thank you.
So we know it goes from 1. When does it hit negative 1?
After it's
After it hits 0. So it hits 0 next at 90 degrees.
right.
Negative 1 at 180. Back to 0. 270. Back to 1.
At 360.
So the only reason I made it stretched out was just so it was easier to see up on the board. So I could work with it a little bit better. So that's, and then it repeats. We know cosine keeps going. So it would look like this. So our question is, why is this going to come out as negative sign instead of positive sign? So let's take the derivatives at various points and look for a pattern. What is the derivative going to be here? At the maximum. And that is correct, 0. Why is it 0 there?
Because the tangent line is horizontal.
Because we have a horizontal tangent line.
The sluffer is back.
you can just put that on my desk.
Okay.
So,
How was playing for your meeting?
we have 0 there. So if we draw the derivative graph on the same set of axes as my position graph, then we have 0 there. Where else are we going to get slopes of 0? Every maximum and every minimum. So we know we have zeros all there. So then let's consider the slope of our tangent lines. What is my slope approximately? We're just kind of guesstimating right now. What's my slope going to be approximately here? Is it positive or negative, first of all? Negative. A little steeper than 1 if we were, well, I guess it depends on, yeah, see, a little steeper than 1 because R1 goes from here to here. So a little, hold on, steepness. Less steep, more steep. And it may just be our drawing. You know, we can't draw it exactly. But we do know it's negative. Are we going to get more steep or less steep as we move down? Is this one going to be steeper or less steep? It's hard to draw so many tangent lines on the same graph. Okay. I think it's going to get steeper until we hit this kind of changing point where it gets less steep. Does that make sense? So we're getting steeper in the negative direction. I'm going to undo these so we don't have so much going on the graph. We're getting steeper in the x direction, so we're getting more and more negative until we hit this middle point where we start getting still negative but less steep. So we were in the negatives. We kept getting steeper and steeper slope, so it gets lower and lower. And then when our slopes start getting less and less steep, we go back up. So what's going to happen if we do our next section? Is our slope here positive or negative? Positive. And then same thing, if I draw another slope, it's getting steeper, steeper until we start going past 0, and then it's less steep. So again, I'm going to get rid of my tangent lines. So we're going positive, steeper, 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 so we're getting higher on our velocity graph because a steeper slope means literally a higher number. So the slope gets bigger, and then we go back down as we start getting less steep. So what piece of graph have we drawn here? What does that look like? It's pretty close to sine, but, so I need one more color. Let's do blue. What does sine start out with? It starts going positive first. It's up first. So we basically flipped our graph. How do we know to flip a graph? What? Trying to think of a good way to phrase this question. In what way could we take any graph and flip it upside down? Flip the entire graph. Do you remember transformations where you had to do, we have a shift to the right, a shift to the left, a vertical shift up, a vertical shift down. What was the way to make a graph flip? And keep in mind, we already know the blue was sine of x, and we know we're trying to find the derivative of cosine x. So what did I change to flip this graph upside down? We put a negative sign out front. So the negative flipped the graph. So that is why it's a negative sign. So let's look at our other trig derivatives. So we're going to do kind of a group activity. I'm going to have you rewrite, so we're going to do one equation per group, and then I'll just provide you the fourth one. We're going to rewrite this as only using sine or cosine, because we know the derivatives of that, and we're going to take the derivative. So like tangent, how can we rewrite tangent as only sine and cosine? Sine over cosine. How would I take the derivative of something like that? The quotient rule. We have to do quotient rule using what we know about sine and cosine. So, Eliana and Stephania. Every day. Seriously, I want to punch myself in the face every time.
A lot of teeth. Whoa. That
That's really
escalated
bad
quickly.
for screwing up her name every time. I don't know why.
It's okay,
So,
we'll
you guys will
tell
do
them.
derivative of tangent. You guys will do derivative of cotangent, and you guys will do derivative of secant.
And you're doing cosine.
Yes.
Oh, good, she's paused it. Okay, now I can.
I'm unique. You guys are just
You're unique.
not cool.
Ouch,
So I want
they
to
have
give
like
you guys
a
just like
falling
3 to
group?
5 minutes with your group to try and find the derivative. First you have to rewrite because the only derivatives we know right now are sine and cosine. And then you may have to use quotient rule. Actually, you will all have to use quotient rule.
Okay.
Yes, you guys are group 2.
We're group 3.
Yes, you are group 2.
Sort of free. So, should we write down all of them because everyone's gonna have to tell us their.
Yes, and we're also going to put them on the note cards once we have them all.
Okay.
But you're only going to have to show the work for one of them, and then the rest we're just going to have the formulas for.
Okay.
That over.
Let's do this. You got it? You got it? Oh, really? Okay, so it's not. So it's just 1 over C times 1 over cosine. Is it no 1 over sine? You sure?
Yeah, I remember because secant was with cosine and cosine with sine. And it really bugged me.
Yes, so far.
So it's 1 over cosine. And then you have to take the quotient rule. Yeah.
Okay, what do we know? Cosine, so no, we would not cancel out cosine squared over cosine squared because of the plus sign. But, think back to trig. Do you remember what cosine squared plus sine squared had its own special?
No, there's no quarter kids. Oh, if there is, then it's not like that. So,
Yep, it's 1. Yep, so the entire numerator is 1. And then we want to rewrite it so it's not a fraction either. Somehow we want to change 1 over cosine
And then you
squared
have
to
1
something
of
else.
everything. And then find the square.
Leave it as 1 over cosine squared because there's another substitute.
Even when I'm in square.
We know what 1 over cosine equals.
Square? Not here.
quarter or basing.
Okay. So we have negative sine squared minus cosine squared, correct? Let's factor out that negative, and then we need to use some trig substitution. If I factor out the negative, I have sine squared plus.
Is it sine that goes to cosine or cosine that goes to
Do you
negative?
remember what sine
Negative.
squared plus cosine squared has its own formula? What if we substitute in a value? I know it's true, so I know whatever value I substitute in, we're getting the
That's
same
not
answer.
simplified. You can make it
So
more
let's
simple.
substitute in 0. What's sine of 0?
Is it cosine of x times 1?
Sine of 0 is
Sorry, what?
0.
So it's cosine of x,
What
right?
about cosine of 0?
Cosine of x, not just
One.
cosine.
So we have 0 squared plus 1 squared. What does that give us?
So this is just
0 squared
cosine.
It's 1. So cosine squared plus sine squared is 1. It wouldn't have mattered what value we put in, we would always get 1 now. We could have done square root 2 over 2. No, 45. Cosine 45. We would have done square root 2 over 2 squared plus square root 2 over 2 squared. We're still going to get 1.
Secant is its own derivative.
You're going to put 1/2 plus 1/2.
When you're doing all
So
of
it's
that?
true every time. So once you factor out that
No,
negative,
I just did that
now you
one.
know
I
it's
said that.
positive sine squared plus positive cosine squared equals.
Can you check my math so I'm not like, especially well, like right there when I simplified it.
That is correct. Wait, hold on. Secant. Low d high. This should have come first. 0 cosine x should come first, and then minus negative sine.
Oh.
So you just need to make that positive answer.
Okay. My bad.
So then you do need to rewrite your final answer. What can we change 1 over sine? This is 1 over
Because
sine.
you have
Oh, it's-
cosine. Where did you get the 0?
Derivative of one.
Oh, duh.
So that's
Negative cosecant x
That's freaking awesome.
squared.
Okay.
Sine
I
squared.
really like it.
So did you remember what 1 over cosine was? 1 over cosine is close.
So does it become negative? Sine
And then
of x
squared
is
will
equal
still be
sine
there.
of x squared.
Okay,
That's times 0.
so
Right.
That doesn't exist.
I may not have paused the recording, I'm sorry. I thought I did, but I may not. So if you do watch this video, there will be a lot of empty space. Okay, group 1, what did you guys get?
Right.
Secant squared. Group 2, what did you get?
That's 10.
Negative cosecant squared. See a pattern between the two?
Is that it?
Tangent and cotangent are kind of they're reciprocals, not opposites. Secant and cosecant are related. What about secant x? What did you guys get for secant x?
Tangent x, secant x.
Tangent x times secant x. And the derivative of cosecant x is negative cotangent cosecant x. Okay, so we are going to make the note cards really quick for these. Okay. So the derivative of sine x plus 1 over secant x. What rule must I use to solve this?
Quotient.
Quotient. Keep that in mind. I know sometimes when you get in the midst of doing problems, you just want to take the derivative of the top over the derivative of the bottom. This is not true. It will not work. You must use quotient rule. So we have u is sine x plus 1. V is secant x. Du dx, or u prime. You can use whichever notation. Derivative of sine x plus 1. Just cosine, because what's the derivative of 1? 0. What about derivative of v? derivative of secant.
Tangent X.
Tangent x, secant x. And you will need to have them memorized eventually. I do not expect you to have them memorized yet. I am going to show you, you should probably have sine and cosine pretty much memorized already. But I will show you kind of a mnemonic, a way to remember how to do these types, or how to remember the derivative of secant, cosecant, tangent, cotangent. So now we apply the quotient rule, low d high. V is our low, so secant x times the derivative of the top times cosine x minus high d low, so sine x plus 1 times tangent x secant x all over low secant x squared. So we can do some simplifying. I know you guys see trig and you're like, oh, I don't want to do anything with this, but we can do some simplifying. I'm going to get this out of the way first. Springs, hey, let's back up like a spring. Okay. I know I'm weird. Okay, so what could I factor out of the numerator right now? We could factor out a secant x. We have secant times cosine in the first piece, secant times all of that in the second piece. So I'm going to factor out a secant x first of all. And why would I have wanted to do that?
Can you now take, cancel?
We can cancel some stuff out. We can cancel secant x on the top with only one of the secant x's on the bottom. And cross out squared. So now I could also distribute my tangent in. We would have cosine x minus sine times tangent minus just plain old tangent over just secant x. So what do you think we should do next? There's something else I can still do to kind of simplify further. What else could I rewrite? What trig substitution could I use? Okay, what can I write tangent as? Sine over cosine. So we have cosine x minus sine x times sine x over cosine x minus, we write this also as sine over cosine. And what can I rewrite secant as?
Isn't that
1 divided by cosine. Yeah, we will. This is a lot of trig substitution. So in the numerator, I could combine some things if I had a common denominator, which 2 out of the 3 already do. What would I do to get the first piece, just cosine x, to have a common denominator? How would I also make this over cosine? Multiply it by cosine over cosine. So we'd have cosine squared over cosine minus sine times sine is sine squared over cosine minus sine over cosine. And then we have divided by 1 over cosine. I'm going to write that to the side. If If I've divided by 1 over cosine, what is that the same as?
Multiply by cosine.
Timesing by cosine. So right now we have cosine squared, man, out of room again, minus sine squared, minus sine x, all over cosine, times cosine. So what can we do again? If we're timesing by cosine and we're dividing by cosine, cancel them out. Now we know what cosine squared plus sine squared equals. We don't have any such formula for cosine squared minus sine squared. There's a lot of trig substitution / fraction work. So we will get a little bit of practice on our trig substitution. I want you to practice at least when you do the assignment.
Will there be a lot of these?
Some will be simpler. So I made up my own. I thought I used an example from the book, but I made up my own. Like, this is not coming out super nice, so we would have to stop here. There's nothing else we could substitute in to combine any further.
Oh, day.
So if you get that point, then you just...
Yeah. So the reason this one didn't, like, most of the ones in the book, they've worked through them and it'll come out as like tangent x or tangent times cosine, you know, something a little bit simpler.
Which is really annoying that they write it out that complicated, just saying.
So we can apply our knowledge of trig now to what's called harmonic motion. Remember spring problems?
Not hot springs? By the way, 300% is bigger.
No, I do not want that. Okay, so we just want to see the word example 2. So weight is hanging from a spring,
Choose the help compromise.
and it's stretched 5 units beyond its rest position. So when it's talking about rest position, that means what the spring would be at without any weight on. Wait, hold on. Sorry, I lied. Rest position is where it is at with the weight on. So this one is our rest position. The spring is stretched a little bit because it has the weight on.
Oh,
Spanish teacher
T.
So now we stretch it further. We take this from rest and stretch it down 5 more units, and we let go of the spring. What's going to happen when we do that?
It's going to also.
It's going to oscillate. It's going to go up and down. So rest position is where it was just at when we had the weight on. We're going to pull it down a little bit and let go. So eventually we're going to figure out how to actually find the formula. There is a formula that we can use with springs. And they gave us a position formula. Position is 5 cosine t. So if I have position and I want to find velocity and acceleration, what should I do? Take the derivative. So I know these ones look hard because it's, you know, word problems, but it just is asking us to find velocity and acceleration. So what's our velocity? We're taking the derivative of 5 cosine t.
So it would be -5 sine.
Negative 5 sine t. Derivative of cosine is negative sine. If I want to find acceleration, derivative of sine is positive cosine, so it's going to stay a negative 5 cosine t. And that's all we're talking about with springs today, just to introduce the concept of taking a spring, stretching it beyond its normal, and letting it oscillate back and forth when we release it. So we just have one more example. I'll show you the kind of nifty way to remember the derivatives of secant, tangent, cosecant, cotangent. And then I'll give you the assignment. This one's a lot wordy, a lot of words to write down for not much math. Yeah. Like I wrote down an entire paragraph for velocity and acceleration.
I was waiting for some complicated thing to take like a page.
No, we'll be able to do more with springs later, but this was just to introduce, really. Okay. So last example. What if I want to find the second derivative of secant? First derivative is easy. We have a formula for that. So y prime, because to get to y double prime, we need the first derivative first. So what is y prime? Secant tangent on this one. Secant tangent. Tangent.
Ooh, backwards.
So what am I going to have to do in order to find y double prime? Take the derivative using the product rule, because this is secant x times tangent x. Anytime we have, again, variables multiplying together, we must use product rule. Just like anytime you have variables dividing, you can't cancel anything out, you must use quotient rule.
Can you only do this on the secant, or can you do the double prime on the others?
You could also do double prime. So we have cotangent or tangent. The derivative of tangent x is secant squared. There is a way to do the derivative of secant squared, but we do not know it yet. We're going to learn that in chapter 4.
So far all we know is this one.
Product rule, quotient rule, power rule, and now the derivatives of our trig functions.
Sweet.
So we will learn it eventually, but we can't do that yet. So, product rule. Derivative of secant is secant x tangent x. Derivative of tangent is secant squared x. We do low d high plus high d low. So low is tangent. Low d high. So tangent times secant x plus tan x. Oh, not plus, times. Plus